seminar is called Working with Compression. In case you don't know me, I'm Fabian Giesen, or Rücker Farbhausch, whichever you prefer. So this is not actually about writing your own compression routines, your own packers, because I think that's something not a lot of people are really interested in. So what the seminar is about is not about doing your own packer, but about, you already have a packer and you want to maximize compression ratio by some techniques. So this is a long seminar. We got 2 parts in a row with a small break in between. So I'll first do the outline for part 1, which is about 40 minutes or 45. Then we'll do a short break, and then we'll continue with the second part. So I'll first do a small introduction, then I'll talk about some elementary techniques for compression, which you've probably heard about, and then we'll look in this section at a small example of how even with very simple techniques you can get very decent improvements in the compression rate and the like. And for the last part, which is rather theoretical, we're going to look a bit into coding. We'll see what that means later. Okay, so first for the introduction. Okay, this is the wrong version of the slides, but I'll use them anyway. 4K and 64K intros stopped being purely about code and coding several years ago. So by now you really don't have things like one effect intros anymore, or not as much anyway, as you had, say, in the mid-90s. It's a lot more complex data, generated stuff, relatively fancy materials, complex meshes, complex shading, textures, and so on. So it's all very much complex by now, and it's also a lot of time you need to produce this amount of data. Because, this just doesn't appear on your screen. You have to work for that. And more importantly, if you are targeting, say, 4K or 64K, it also takes a lot of space. But luckily, packers have gotten a lot better lately. So when you have, say, Crinkler, you get really, really spectacular compression ratios for 4Ks without batch file droppers or the like. So this kind of basically hacks you would have in 4Ks still a year ago. And Crinkler actually has better compression than this kind of hacks, while still being a normal executable that you can really just use everywhere. And similarly for 64K intros, I'm talking about Crunchy here because I'm most familiar with that because it's my own packer, but it goes for others as well. The current Crunchy version packs FR08 into about 50.5 kilobytes, while the final version was 63.5 kilobytes. So over the last 5 years, packers have really gotten a lot better. I mean, this is almost a quarter smaller of the old size. So there's really quite dramatic improvement in packet technology over the last few years. This not only goes for Crunchy, but basically for everything you would use in the scene nowadays. But if you want that kind of pack ratio, you can't just do it however you want to and just hope that it will get small later and when you use a packer. So to get good compression, what you actually have to do is you have to make sure that the data is in a format that manages to compress well. And the problem about that is that to do this, you need to know how packers work, basically. What kind of tricks they employ to make data smaller, how they compress things, and this is something not a lot of people know about. You don't need to know the whole details, what exactly is it coded like, how to get certain decisions made. This is not really important, but you do need to know where the compression is achieved, what compresses well, what doesn't, and what kind of things the packer is looking for to make things smaller. And this is the type of questions I'll try to answer in this seminar, together with the question of how to make it, of how to arrange data in a way that maximizes compression ratio. And I'll assume you have some basic knowledge of C syntax. This is actually not so important anymore because I removed the slides that had any kind of code in it because they were not really relevant. You do need some programming experience. I assume you have coded some intros or some intro-like stuff before. because I'm making references to stuff you can only know if you've ever done an intro. And I have a really, really small number of mathematical formulas in there for those who are interested. It's nothing you need to understand this talk, but if you are able to understand it, fine. This is just a bit more precise than what you would get from my explanation alone. Okay, so for the elementary techniques session or section. The first one is simply run link encoding, and I think every one of you has already done this already. This is really, basically the technique that's mentioned first in any kind of data compression text, and most people already discover it by themselves. What you do is you have a text file or whatever image, and you try to replace runs of identical symbols with a pair that says how often that symbol appears. For example, here you have the string AAA, A, B, C, 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 and it's 5 A's, 1 B, 3 C's, so that's what you encode. This is simple and fast, but it doesn't really work for most types of data. For example, in text data, you really can't expect any kind of compression from this because virtually, in normal English text, virtually no letter gets repeated gets repeated more than twice in a row, which is where you would gain. So this is only interesting for specialized types of data, for example, palletized images and stuff like that. It is often used as a pre- or post-processing step for other algorithms, because when you have such long runs, a lot of other methods get either very slow or have certain problems. So you can get this kind of problems away by combining this method with run link encoding. So this is where it's used. And another very common variant, for example, a variant of this is used in JPEG, is that you don't code runs of every symbol you have, but only of one special symbol, which is usually 0. So you have a lot of values which are 0 and some who are not, and you just code, well, here's a real value and then there's 5 zeros in a row. So you only use run codes for one special symbol. And this basic encoding I have here, which just appends a count after each character, basically just sucks. That's the kind of encoding you see in textbooks and the like when the method is explained, but it's not something you would use. I'll look into some other encodings, because this kind of coding becomes interesting later on when you see extensions of that. So the first upgrade you can do is you can use a packet-based scheme, which means that you don't store run counts for everything. You assume that there's only a few characters which are actually repeated, and the rest is basically just copied over, because there are no runs in there. So what you do is you group this data into so-called packets, which have a variable size, which you determine during packing. And each packet has a size, and it can either be a copy packet, which just says that those end symbols which follow are uncompressed, and you don't do anything with them. And there's also run packets, which means, there's just one character code following, and please repeat this character n times. As said, this is useful, for example, for palletized images, where you have large solid color areas. That's the kind of stuff that gets compressed with run link coding, and so it's used in some old graphics formats. And another variant to extend this is to use so-called escape codes, which again assumes that most of your data doesn't have runs, because as I mentioned, this usually doesn't appear in real data that you have a lot of runs in all kinds in big sections. So this is assuming that you have an unused code value which you're not using, and when you use that code value to mark, okay, now the run following, so this is a character that's repeated a few times, and if there are no runs in there, you can just store the data as is without this escape code, and everything is fine. This is nice because it doesn't expand any uncompressible data, assuming that you have one word that isn't used, a code word, but it reduces compression gains because every run has to be tagged specifically with that escape symbol. So it's both of those don't really make run link encoding a scheme that's practical for real-world applications when you want real compression. And I mentioned those, as I already said before, mainly because extensions of these types of encoding, of these ideas, will become important later on. Another very, very well-known scheme in data compression, I assume most of you have at least heard of that as well, is delta coding, which is not an actual compression algorithm, but is a transform. So it doesn't try to make data actively smaller. It just changes the data in a reversible way in the hopes that that you can compress it better afterwards. And what you do, assuming you have numerical data, like for example sound samples here, and you don't code the symbols themselves, but the differences between adjacent symbols. So the first symbol here would be a 1, because there's nothing in front of that. We just copy it over. Then we have 2 1s here, which don't get, there's no change from the previous symbol, so those get zeros. Then you have a small increasing sequence here, which just maps to 1 1 1 1, and a jump here, which is -3. And as you see, what's this noise? Okay, it's gone. As you see, this had basically no runs or repetitions in it, but this is already a lot easier to compress because they are bigger runs. And it's good for that type of data, which is smooth data that varies slowly. So values don't change it abruptly, don't jump around all the time. For example, sound samples again. Those usually vary only by a small amount each sample point. So you get an improvement there because the differences are smaller than the actual sample values, and they tend to cluster around 0. And we'll soon see how we can take advantage of the latter, how that can make it more interesting for other compression schemes. And again, it's very simple and fast, and not much use for, say, textual data or binaries. So, quantization, which in this context strictly means using less bits to represent your values, for example, numbers. And it's the main lossy step in all kinds of lossy compression algorithms, say, for example, JPEG again. There are 2 main variants. One is scalar quantization, so-called scalar quantization, which is just, using less bits for each individual number. None of those values are grouped together, or you don't exploit similarity between those values, but you just code each number on its own. There's uniform quantization, which means that, the differences between samples are always the same. And, for example, when you have sample sound again, you have 8-bit versus 16-bit, so the 8-bit is basically a quantized version of 16-bit sampled sound, or high color images with 15 bits versus true color images with 24 bits and the like. So it's always basically just cutting off bits. And that's how it looks. It's very simple, and it usually also produces very noticeable errors. And then there's non-uniform quantization, where you try not to make everything get the same step sizes, but try to make ranges that are important to you. Give them more range, so you can have a finer resolution there. For example, in floating point values, you give the values more precision near 0, because when you have a value on the magnitude of, say, 1 million, a difference of 0.1 isn't really that important. It doesn't change that much. But when your values are very small, like say 0.001, a difference of 0.1 is huge. And what floating point values do is that they give more precision to smaller values, and they divide this non-uniformly. And there are other examples you probably haven't heard of yet, because it's not that popular actually. And then there's so-called vector quantization, which tries to code several values at once, which tries to group them. It uses a so-called codebook. So it's basically a table that tells you how what a certain value means. You have a table of a few entries, and those just lists what values it gets mapped to, and it needs to be stored, which is typically quite small. An example would be, again, palletized images. You have this table of 256 colors you use, which are actually 3 values, one for red, one for green, and one for blue. And you use those 256 colors out of the whole RGB color space, and you compress this data from 24 to 8 bits. So it's it's a factor of 3 to 1, and decoding is basically a table lookup. And some older video codecs, like for example Intel Indio codecs, do a similar thing with groups of pixels. So they have, say, 4x4 pixel blocks, and they try to assign codes to those and just use a few of them. So yeah, everything gets small. And in an intro context, scalar quantization is usually fine. You don't need to get fancy. You don't want to get fancy because it makes everything more complicated. You get hard to find bugs. You get data that looks very random to any packer that runs after it. So you try to keep your code simple, and you want to keep yourself happy. You don't want any complications except coding the intro itself. And one such example for a very, very low cost quantization that really saves a lot of space is just throwing away the least significant byte of 32-bit float numbers. This reduces the mantissa size from 23 to 15 bits. If you don't know about floating point numbers, there's basically two components to them. One is the so-called exponent, which tells you what value range this number is in. I already mentioned you have very small numbers and very big numbers, and this exponent tells you what range it is approximately in. And this mantissa is the value which tells you where in that range the value is. And just reducing that mantissa size means, yeah, you have less resolution but the same value range. And it's usually fine for most data. Or you could also use so-called half floats, like you have in CG or HLSL, high-level shading language, which is a 16-bit floating point format, and it's also usable for lots of cases. And another example would be, say, for camera splines, where you usually have a lot of keyframes at a certain frame, or which is either in frames or milliseconds or whatever you use. And yeah, you have those time values stored and the key values where the camera is at that point. And what you can do is, yeah, that you just store how long the whole spline is, and then just say, well, the start point of the spline maps to 0, the end point of the spline maps to 1, and you just code the time in between with a single 12 or 8-bit value. This means that the keyframes aren't positioned as exactly, but it usually, yeah, still is enough for, say, camera runs and so on. So this can save you a lot of space, especially when you use, say, 32-bit numbers before. And stuff like that is quantization. And if you do quantization, it's important that you round everything correctly, because this can cut quantization error to half, because if you always round into one direction, yeah, well, errors accumulate in that direction. For example, in Candytron, I was always rounding towards the left side, and so the face of the main character was very unsymmetric, because everything just got snapped left. And in the final version, I just, yeah, fixed the rounding to something more sensible, which was, yeah, say, a line of code. And it really, really made a difference in appearance. So you need to take care of that if you do quantization. And yeah, the final one in this elementary techniques section is reordering, which is probably the simplest technique of them all I mention here. And it's the most important one for practical applications, because this is really where you can get, yeah, the biggest improvement in pack rate with the least effort. For example, in Crunchy, my exe packer, I reorder the way instructions are stored, instruction opcodes are stored. And when you pack this with the Crunchy compression engine, for example, for Krieger without reordering, you get about 78 kilobytes. And after this reordering step, you're down to 65. So when rounding correctly, that's about a 12K difference. And this is just by reordering the sequence of the bytes. I didn't change any of the values themselves, just the order in which they are stored. So this can really, really make a huge difference to your compression ratio. And we'll need some more background info to see how that works and how we can design such stuff. That will be in the second part of this talk. And right now, I'll just give you a broad overview what you have to do, which is grouping data by context. Things that mean similar things, affect similar values, should probably be stored together. That's the main concept. Everything that's similar in meaning is probably also similar in value. So when you have this structure of what different values mean into consideration and pack that into your data format, you can get a big improvement in terms of compression, because it makes the packer has the ability to see much more what is going on, and that these are all similar values, and compress them better. And it also increases efficiency of delta coding and other simple schemes like one-name coding, because when you have similar values all over the place, those differences get small, obviously. So you get even more compression from that, additional compression, at a very low cost. And that's pretty abstract right now. So don't worry, we'll have a lot of examples later on. And a big example now, which is the V2 modules. For those of you who don't know, V2 is the Farbrash synthesizer, or real-time synthesizer, which we use basically in all kinds of intros and even some demos since FR8. So music you do with V2 gets stored as so-called V2 modules or V2M files. And these modules have two main parts. There are patches, so-called patches, which is just terminology, which is basically just instrument definitions for the soft synth. Like, how is everything set up, how is the sound set up. And there's the actual music, which is a MIDI data stream. MIDI is a standard format for music, for those who don't know, and it's just reordered and simplified. So this patch data, the instrument data, is basically unprocessed in storage. So we won't look at that again, because basically everything you change in the user interface gets mapped directly to a byte that change in the value, and there's nothing interesting going on there. But the music data is a lot more interesting, and there's a lot of magic going on there to make it compress well. For example, this music data is stored as a list of events. An event is something that is everything that means the synth has to do some work, like change a parameter, play a note, and stuff like that, or change the instrument. There are two types of events, which are channel events and global events. Channel events only affect this one MIDI channel they're played on, which is like note commands, volume changes, and so on. And there are global events, which are basically there because the Virus 2 is not the standard MIDI instrument like you would usually have, but also has some mastering filters and post-processing effects. So that's what gets controlled by the global events. And every event has a timestamp and some additional data that is depends on what type this event is. And these channel events are grouped by their type, and each of these groups is stored separately. There are notes, a set, both actual notes and note off commands, so just play a C5 and that kind of thing. There are so-called program changes, which just change the instrument currently being used in a certain channel. There's pitch band, which is again just MIDI terminology. It's just a value you can use in your sound to change the way something sounds. This is up to the musician to use this or not, but this is a different stream. There are controller changes. A controller is something like velocity, loudness, modulation, and so on, all again stored separately, and again grouped by this type of the controller. So we've already done some reordering there because we've separated everything into global and channel events, and we have some further grouping for the channel events. The question would be how much it saves us. For the FR8 main tune in MIDI format, you have about 21 kilobytes after packing with the Crunchy compression engine. And I'll always use packed sizes from now on when I mention any specific size, because that's what's really relevant to us. We want to improve compression ratio, not the size of the original data before compression. And if you use this encoding I just mentioned, so basically a prototype V2M format, you land at about 82 kilobytes, which is not as good as we might have hoped. So the problem is that we store a lot of information. For each effect, we have a timestamp which says us where it happens. This timestamp is very big, and we store all parameters explicitly. So it's very easy to play, but it's not optimal for compression. So there's a lot of stuff we can do to make it compress better. And The first thing we'll be looking at will be timestamps. Because those timestamps are set 24-bit numbers, we could have used any other size, but yeah, 24-bit is what we picked. And yeah, as these events happen over the whole music, the time just goes bigger and bigger because I mean the piece of music is basically just a sequence of events, and you can easily order that. So you don't actually have to store complete timestamps. They will always increase, so you can easily delta code them, and the values will get smaller because events are close together usually. And when you do that, when you just do delta coding for the timestamps, you're down to 11 kilobytes from 88. So this is a huge improvement from what we originally had, with a minimum with a minimum amount of work. And similarly, you can do this for the command parameters, which can be both node numbers and volume changes and so on. And most of that very smoothly or gets repeated a lot during the music, during the run of the music too. So we can delta code them as well. And if you do this on everything, you're down to 4.5 kilobytes, which, looking at the fact that we just did a few subtractions to get there, is really quite amazing. As you might remember, we started out at about 21 kilobytes. So it's really a minimum amount of work we've done so far. We've already have about a factor 4 reduction in compressed size. And from there, we can try to do some reordering. And what we did for alpha weight was reorder those event bytes as well. Because in the format I described, you have a list of events, and each of these events gets stored separately. You have a 3-byte time delta value, and the 2 bytes of parameter delta values, and they just all get stored in a row. And what we do now is basically we store the first byte of each event, then the second byte of each event, third byte of each event, and so on, and then the 5th byte of each event. That's what we do. So if you would print it out as a table, what we did was basically just rotate it by 90 degrees. That's the idea behind this, is that, for example, for time deltas, most of those will have zeros in their higher order bytes, because most events are close together, so you get long runs of zeros. And usually a lot of parameters are either used or just stay the same over a long time, so again you have long runs of zeros there. That's the idea. But as it turns out, with this kind of reordering, we have about 300 bytes bigger than the original version. Well, oops. And this is the reason why you should always test this kind of transform separately. What happened here was that we did the reordering and the delta coding stuff at the same time. So we didn't even notice that this reordering stuff actually makes everything bigger until I started preparing the seminar, that is. So what you can see from this example both is that it's how much difference it can make to make really simple changes to the way you store your data. And it also shows how important it is to always measure if something makes a difference, how important it is, if it's worth it, and that kind of thing. And none of the transforms I will mention here or I can recommend are complex ones. It's always very simple stuff like doing differences or just reordering stuff. More complicated stuff can give you maybe another 10% improvement over the really, really basic changes. But it's a lot more code, and the fancier you try to get, the more you have to assume about the type of data you're doing. This kind of thing, like just delta coding, you can basically do without even knowing what type of data you're looking at. This is just a simple routine that does a few subtractions. The more you get specific to the type of application, from that you can get a lot of more improvement. But it also means that you can reuse it elsewhere. And this is more code, and unless you really have a lot of data of one particular type, it's not worth it. Anyway, there are other compression algorithms, and I apologize for the fact that it's all very theoretical right now, but yeah, this is basically just something we have to get over, so I can actually explain to you, and so you can see why certain things work and why others don't. And this is the third chapter, which is coding. Actually, I'm not talking about an arbitrary type of coding, but so-called binary code. Binary code is just a table like this one here, which just tells you which character, which symbol gets mapped to which bit string. This would be a certain example. If you prefer the mathematical notation, you could just call the function from the alphabet to a bit string, but you can do that, but it doesn't really make a difference. And when you have a string of symbols you want to code, for example here this AABC, you just look the A up, which codes to 0, so you get a 0 here, and another 0 because you have another A, then the B, which is coded to 1, 0, and 1, 1 for the final C. So it's very simple. And if you can get from this kind of bit string back to the original string uniquely, then it's called a uniquely decodable code, which is very important for us because, any kind of coding you can't reverse, you can't decode, it's useless. And another definition is the so-called prefix code, which is basically a code you can decode from left to right without having any kind of look ahead, like what happens in 5 characters from now on. You can always tell whether you're at the end of a code or not. This is not a formal definition, but it's enough to get the picture of what's going on. And this example code is a prefix code actually. And for all those uniquely decodable codes, any kind of uniquely decodable codes, there's a prefix code which has exactly the same length for every single character. It's not the same mapping, but it's exactly the same length, so you get the same amount of compression. So we can limit ourselves to prefix codes and enjoy the fact that they're easy to decode. But this doesn't solve the problem of how to get good codes. There are, for example, rule-based codes for certain types of value distributions, like the unary code, which maps 1 to 0, 2 to 1, 0, 3 to 1, 1, 0, and so on. It always just gets another one inserted at the front. It's always a string, as long as the number you're trying to code terminated with a 0. So, very simple. And there are fancier codes, again, for specific value distributions. And if you have a value that you know beforehand, to have a specific distribution, it's fine, you can use that code. But in general, when you're doing lossless compression, you don't know what kind of data you're going to get beforehand. So you want to generate them from your data, which brings us to so-called Huffman coding. This is one of the classic algorithms in computer science, and it's basically taught in every introductory computer science class. This algorithm gets the occurrence counts. How often does each single character occur in a text file, for example, and the so-called frequencies of individual symbols. And what it gives you back is an optimal binary code for that distribution, which means that no binary code, no matter what you do, can be better. They always have to be at least as good, at least as long as the Huffman code. I won't describe how to do this. It's not really difficult, but it's not really interesting in this context either. What's more important to us is what type of redundancy gets exploited. What this does, it assumes that certain characters appear a lot more often than others. For example, in English text, E's are a lot more common than, say, K's. So you would assign a shorter code to the letter E than you would to K. And similarly, if you have delta-coded values, I mentioned that those values tend to cluster around 0, tend to be close to 0. So you would assign shorter codes to values that are near 0. And Huffman codes are great for that. And another improvement would be so-called arithmetic coding, which is a bit of a problem because I said before that Huffman codes are optimal. which is partially true. They're optimal binary codes. But if you don't restrict yourself to binary codes, so each character gets gets one single bit string that it represents, you can actually do a bit better. And the key problem with binary codes is that you always get bit strings with whose length is you always allocate whole bits at once, which is kind of weird if you think about it, because what the hell are partial bits supposed to mean? Say you have a string of 3 symbols A, B, C, and all of those 3 are equally likely to happen. If you generate a Huffman code for that, you get a code like this one mentioned. A set A gets mapped to 0, B to 1, 0, and C to 1, 1, or some permutation of that with the lattice exchanged or the bit values flipped, but it will always be something with those code lengths. And say your input string values is 3 n characters long, so you have n A's, n B's, and n C's. The coded string will be 5 n bits long, because this A character, which takes 1 bit to code, occurs n times, and the other 2 characters, which take 2 bits to code each, also occur n times. So you end up at 5 n bits. And you can also try something different. You first assign numbers to those codes. So A is 0, B is 1, and C is 2. And if you do that, we can stuff 5 characters into each byte. So we have those 5 characters, C1 to C5, and you calculate a value from that. You do C1 plus 3 times C2 plus 3 squared times C3, and so on. What you're basically doing is you're writing this as a number, like you would a decimal number, just at number base 3. And if you do that for bytes, you use 243 out of all 256 characters, which is not a very good usage. There are still some of those that are free, but it's enough to make my point. And decoding this is several divisions, or you could just do a table lookup, which tells you for each byte value which 5 characters these are. So you can code 5 characters in 8 bits, or so we have 8 bits per 5 characters, or 1.6 bits per character. And this is where the fractional bits start to appear. And when you calculate that, you have your string of 3 n characters length, and you have 1.6 bits per character, so we get 4.8 n bits for the whole string. That's 0.2 bits per character less, and that's how you get fractional bits. You still get something that has a byte size, but the average length, this is all just average length, is smaller, so you get a compression ratio improvement. The idea is, in this kind of scheme, to treat this byte stream as a number, which you can do arithmetic on, which is why it's called arithmetic coding. You can multiply, you can add, and obviously it's not a very good idea to do any kind of calculation with a 400 megabyte number, like you would have for a really large packed file. And different arithmetic coding algorithms try to do a lot less work, and work, say, with only a 32-bit number, and maybe lose some bits by doing some rounding in between, but they try to do this efficiently. But still, this is a lot of calculation per byte or per bit coded, so this is slower than binary codes, and noticeably so. One of the improvements you get from this, though, is that you're not working with code strings anymore, with individual characters that have a certain number of times it occurs. All you really need to do this kind of coding is how probable it is that each of those characters happens in your text file or whatever. And unlike Huffman coding, where you have to regenerate a tree every time the count of characters changes, you can change this distribution of what is how probable quite easily, which is called adaptive arithmetic coding. And you can even go a bit further and use different models, different sets of what is how probable based on the context, which Again, I'll define more precisely in part 2. But the basic idea is, for example, when you have an English text again, the character U is very probable if the last character you've seen before is a Q. Because in English text you always have QU. There's basically no other letter that can appear after a Q in normal English text. So if the last character you've seen is a Q, you can use a different mapping of probabilities because the U is very, very highly probable. And with that kind of stuff, you can get a lot of compression improvement by using context. Again, trying to put more information, more knowledge about what has happened in the data before into your coding process. Anyway, this is already quite a lot for the first half or first part of the seminar. So do you have any questions so far? Nothing? I can't believe every one of you has no questions. Yeah?
I was just wondering, when you were comparing the Park age sizes of your two sound files, did those sizes include the algorithm to expand it again, or was it only the compressed data?
No, that was just the compressed data. The DPack has about 300 bytes. Okay, again, it's usually in the executable packer you use, so this is not really a cost you see, because it's always there anyway. Yeah. Any other questions? Yeah?
So which compression algorithm do you use for finally after the data coding and reordering?
I'll come to that in part 2, at the very beginning. Okay. No more questions? Okay, then we'll do a short 10-minute break or so, whatever you prefer here. And then we'll go on with part 2.